It is the last day of March. 2 weeks from today is when you have to have your project poster turned in by 3 p.m. 2 weeks from today, on Friday the 13th. 4 weeks from today. 4 weeks from today is the last day of the semester. At which point, anything that's going to be graded, which in your case would simply be any other lab reports, is going to have to be turned in. And then we have the final exam the following Tuesday, and we'll be all done. And then it will be summer to regroup for next year. So let's start the day with a clicker question. Which statement is not true about relativistic momentum? So 2 of these are correct statements, 1 is untrue. And I'll put the vector sign, it still would be correct without it, but this is more correct with it. Well, that's stupid of me now, isn't it? Okay. Getting down. I am getting internet connection right now, so I believe it is. Okay, I don't have answers from Michaela, Angelina, Ashley. Okay, I'll give it another 5 seconds and move on. No luck there, Ashley? Okay. Well, the answers we had here are 1, 6, and 10. Now, instead of calling on you, since I already said something and then I acknowledged, well, that was a stupid thing for me to say, the correct answer was the majority answer here. Right? I was putting the vector signs on so you didn't say, well, we've got a problem there between the vector and not having vector signs. Why is C incorrect? That's the classical momentum. All these statements are true for classical. What?
It still needs gamma.
It needs the gamma. So the relativistic momentum has the gamma in there. Why didn't we worry about that from the get-go when we learned momentum? What value does gamma have if your speed is 100 miles an hour? 1. So why would we put the gamma there? We just didn't put it there because gamma was 1 for all cases until this chapter. So that's why we didn't write it there, but this is correct. So this is always correct. Momentum is always gamma mv. It's just we didn't worry about it until we get to things that are going like 1/10 the speed of light or faster. So we generally only use relativistic calculations when we're 10% the speed of light or faster. Actually, I generally go with 0.1 C or faster. Because if you're 0.1 C or faster, then the relativity is going to make a difference of 2% or more. It's going to start making a noticeable difference. If you're less than 1/10 the speed of light, or 0.1 C, then it's really no difference. And why worry about the hassles if it's not going to make a difference in your outcome? Now, we talked in the last lecture about Newton's second law relating to force. Newton's second law is not this. Instead, we had to use the true definition of Newton's second law. I'll put the net there just to make it more correct. That the net force is equal to the change in momentum over change in time. That's the true Newton's second law. And so that is still correct. It's just our approximate form that net force is mass times acceleration that's going to break down. This actually has important implications. Since momentum has a magnitude of gamma mv, if your momentum is infinite, what is the speed going to be? The speed of light, because gamma goes to infinity as speed approaches the speed of light. If the speed goes faster than the speed of light, what does gamma give you? It gives you an imaginary number. So gamma is not even a real value at speeds exceeding the speed of light. And as you approach the speed of light, the momentum approaches infinity. This has some important implications. We know that change in momentum is the net force multiplied by change in time. If I want to apply a force over a time, in order to reach an infinite momentum, that is the speed of light, I'm going to have a finite force multiplied by an infinite amount of time. So that in and of itself tells you no matter what your force is, you're not going to be able to reach the speed of light with anything that has mass. So just using some logic with Newton's second law and our now new form for momentum allows us to make a statement that says, according to our relativity, nothing can reach the speed of light. But we have to step back just a bit and say, except light. So nothing that has mass can travel at the speed of light is the true statement. If it doesn't have mass, well, then this m part breaks down here in the momentum equation. We're going to learn a new equation for momentum for things without mass. Because light has mass, believe it or not. Or not mass, it has momentum. So now a regression into units. We learned about the electron volt when we started talking about using two parallel plates with different voltages to accelerate an electron. And we said, well, the work done is equal to the force times the distance. And then we were able to say, well, the force is the electric field times the charge, and the electric field times the charge times the distance is the voltage difference per charge times the charge. And so we said, well, we can just say the work is equal to the voltage difference times one electron charge, and we start talking about the electron volt to make it so it's real simple. If I have an electron that goes through a voltage difference of 10 volts, it will have a change in energy of 10 volts times the charge of one electron. We say that's 10 electron volts. When we talk about relativity, we love to use the electron volt as our unit for energy. Not only do we use it for energy, we use it for mass. And you might be saying, wait, energy and mass, different units, right? What are the standard units for mass? Kilograms, the standard units for energy? Joules, right? Different standard units. Well, what we do is we say that, and this is like on the next slide, according to Einstein, rest energy, is equal to mass times the speed of light squared. How many people have seen E equals mc squared? I'm guessing every hand will go up here. The E in that equation is the rest energy. It's not the total energy, which is what E usually stands for us. It's the rest energy. So if I have a particle at rest, like my body, I'm at rest here as far as we can tell. I have an energy that's equal to my mass multiplied by the speed of light squared. So my mass is roughly, well, let's not worry about my mass, but we can calculate my energy and find right away my energy is enormous. My rest energy. That is, if you could harness all the energy in my body, you could run the world for a long time. We'll have to learn how that works coming up in a few lectures from now. But that gives us mass can be written as the rest energy over the speed of light squared. And so for an electron, for instance, the rest energy for an electron is 511 kiloelectron volts. So the mass of the electron is the rest energy over c squared is equal to 511 kiloelectron volts over c squared. So the mass is actually not shown in electron volts, it's in electron volts divided by c squared. But that makes life real simple for a lot of our calculations, and as with everything else in physics, we do things to make it as simple as possible, to make the math easier. So we are going to use the electron volt pretty much exclusively to measure energy as well as mass in the coming days. And this is something you've seen before. 1 electron volt is charge of 1 electron times 1 volt, 1.602 times 10 to the minus 19 joules. And so here is the calculation I just did for the mass of an electron. Moving on. What's the momentum of an electron moving at a speed of 0.80 c in terms of kiloelectron volts per c? How do I find the momentum? Okay, so I'm going to need to calculate gamma, and then I can put it all together. So gamma .8 squared. Remember, we did this before. That's judiciously chosen because 0.8 squared is 0.64. 1 minus 0.64 is 0.36. Square root of 0.36 is 0.6. So gamma is 1 over 0.6. So the momentum is equal to 511 kiloelectron volts per c squared times the velocity 0.80 c times gamma 1 over 0.6. 0.8 over 0.6 is 4/3. Notice my c's here. 1 c will cancel. And I'm not even going to take the time to multiply it through. It's 4/3 of 511 kiloelectron volts per c. So we express momentum in units of kiloelectron volts per c, energy in kiloelectron volts, mass in kiloelectron volts per c squared. Is that an easy or hard concept? Very non-committal. At least a couple of people said, eh. I had about 4 answers. Hopefully that's an easier concept there. It's just a new form of the units to make our calculations easier. The whole point is to make calculations easier. A problem now, a much more significant, serious problem. Carbon dating is based on the radioactive decay of carbon-14 nucleus, that's 6 protons and 8 neutrons, into a nitrogen-14 nucleus, 7 protons, 7 neutrons. In the process, an electron, E-, and a particle called an antineutrino are created. The reaction is written as shown below. Now, we are not into the chapter on radioactive decays yet, but I have to point out some things here. How many electrons do you have in the nucleus of a carbon atom? How many electrons do you have? 0. There are no electrons in the nucleus of the atom. That carbon-14 has 6 protons in the nucleus and 8 neutrons in the nucleus. And then if it's neutral, how many electrons are orbiting the nucleus? If it's neutral, it has 6 protons, 6 electrons. Right. So the carbon-14 atom has 6 electrons, 6 protons, 8 neutrons. It becomes a nitrogen-14 atom with a plus. How many electrons do you have if you have a nitrogen with a plus? 6. So we have the same number of electrons orbiting the nucleus. But we're also having an extra electron. Where did that electron come from then? We stole it. It's not the right answer, but it's a reasonable answer. That electron was created. It did not exist, and now it does. Somewhere along the line, you probably learned of conservation of mass. Now we have to unlearn that. Conservation of mass is untrue. We have conservation of energy, not conservation of mass. But that electron was created. How was it created? It was created in a complex interaction. The nucleus had 14 particles, 8 neutrons, 6 protons. 1 neutron disappeared. If you look back here, we have a diagram that says what protons and neutrons are actually made of. This here's the neutron. Okay. It's a neutron. It's DDU. It's made up of 3 subatomic particles we call quarks. So it's a down, down, up. So it's a down, down, up. A proton, shown here, is an up, up, down. So what's happened in the nucleus is you went from having, having a proton to making another neutron. Is that right? No, that's the way around. You convert a neutron into a proton. So your neutron, the up, down, down, became an up, up, down. That required an interaction to convert, and I say convert, to annihilate a down. You had a down meets an anti-down. And when antiparticles meet, that's how we can convert mass into energy. So when a down meets an anti-down, they annihilate. They're destroyed and they just release energy. But that energy in this decay produced something new. That energy produced, of course, it produced the up to make it into a proton, and it produced an electron, and it produces that electron antineutrino. So you had a down meets an anti-down, it produces an up, an anti-up, the electron, and the neutrino. We don't have the quarks listed here because, well, special things going on there. So this is our equation, but it's a little more complicated than it looks. So we'll get to this. This is the last thing we'll be covering this semester. So right now, we just want to look at the energy released by this reaction. So what we do is we say, what was the mass we started with? What's the mass we ended with? We call this calculation the disintegration energy, Q, the disintegration energy, the energy released when it disintegrated, is just going to be the mass of the, well, you started with an energy of mc squared. Let's just do it in long form. Energy initial is equal to the mass of the parents times c squared. What are the parents? It's just carbon-14. So that's the energy we started with. The energy we end with is mass of the daughters times c squared. So the daughters, that's these 3 things. So there I put the 3 things. I have a nitrogen minus and I have an electron. A nitrogen, or not my nitrogen minus, nitrogen plus. The nitrogen plus is missing an electron. So if I combine these two together, that's just the mass of a nitrogen-14 times speed of light squared. You do have to account for the electrons, but if you combine these two into one, that mass is equal to the mass of a neutral nitrogen-14. And what's the mass of the neutrino? Well, Alex, you're close enough. It says up there in the, see where it has the up, down, so on. To the left of that, it has some like electron and the electron neutrino. What does it say for the mass of the electron neutrino? Yeah, I'm close enough now I can read. So somewhere between 0 and 2 times 10 to the minus 9 giga electron volts per c squared. Notice the mass is given in units that have electron volts per c squared. Somewhere between 0 and 2 times 10 to the minus 19 giga electron volts per c squared. Now, what are the masses of the carbon and nitrogen? They're listed in atomic mass units. Well, atomic mass unit, I can convert that into kilogram, but I don't want to. I'm petulant. Why don't I want to? Because it's a whole lot easier to use this conversion. One atomic mass unit is 931.48 mega electron volts per c squared. So what I'm going to do here is I'm going to calculate the disintegration energy Q is equal to the energy released. How much energy is released? Well, the initial minus the final is going to be what was released. So now let's just put in our numbers. I have the mass of the parent was 13.49s and a 50. The mass of the daughter, 13 and 3 nines, 234. Plus, well, 0 to 2 times 10 to the 9 minus 9 giga electron volts per c squared. I covered the neutrino there. Why did I put the neutrino there? Only God knows. You'll see in a second why it doesn't matter. So there's the full calculation. Now I'm going to split this out into the reasonable part. So if I multiply, or if I separate out the ones that have U from the ones that don't, I'm going to have this 0 to 2 times 10 to the minus 9 giga electron volts. And then I just have to do the subtraction. 13.999950 minus 13.999234. 95 minus 23 is 9. So it's 0.000716. Is that right? Yeah. Well, I gave myself enough space. I'll put my conversion factor right here. (931.8 MeV per c). Oh, 48. Excuse me. MeV per c squared per U. So now my U's cancel, and I'll have it in units of electron volts. And now I simply have to multiply through. So 0.000716 times 931.48 is Now I changed it from giga electron volts to MeV in this last line. And you see, how does this value compare to this value? How does the mass of the energy of the neutrino compare to the disintegration energy otherwise? Just asking you to compare two numbers. What? Whoa. How does 6669, excuse me, compare to somewhere between 0 to 2 times 10 to the minus 6? It's much, much bigger. So that the 0 to 2 times 10 to the minus 6 is going to be a negligible value. So we actually never calculate the energy associated with the neutrino in these calculations because it's so small. The neutrino's name tells you that. Neut, it's neutral, it has no charge. Eno is the diminutive suffix telling you it's tiny. So the neutrino, there are neutrinos flying through your body right now. They just fly right through because they're neutral and they have virtually no mass. They just don't interact with anything, they just zip through. They do have some mass, but it's super tiny. And so we have the disintegration from this problem, 0.6669 mega electron volts. Now we're going to be doing a bunch of these calculations in upcoming chapters. This chapter we won't be doing too much of it, but it's an important idea for later on, understanding how Einstein's idea of energy and mass can tell us about the energy released in this radioactive decay. It released this energy. What if it had been a negative value? What would that mean? It would be, okay, we have two words, exothermic and endothermic. What would it be if this was a negative value? It'd be endothermic. You'd have to put energy in to make it happen. The carbon-14 creation is an endothermic reaction. It requires neutrons with high energy to collide with nitrogen atoms. Neutron gets absorbed, makes an unstable nitrogen-15, which decays into the carbon-14. So the decay is exothermic, but the creation of the nitrogen-15 is endothermic. All right, invariants. Two students here, Alex and Corso, have learned about an invariant, something, a quantity that is invariant in any reference frame. So Alex and Corso, what was that quantity that you learned that was invariant in any reference frame?
It was a lot of math ago.
It was Tuesday.
It was a lot of math ago. I didn't say it was a long time ago.
Okay. The invariant that they learned was if you have a flash of light and you measure the radius of the sphere as it emanates outward, the radius of that sphere in any reference frame should be the speed of light multiplied by the time in that reference frame. But you can also get it using the Pythagorean theorem in 3 dimensions of x squared plus y squared plus z squared. And so the invariant that they learned was, let's take these two calculations for the radius and subtract them. That gives you 0, which is clearly going to be invariant. So the one invariant that they learned was c squared t squared minus x squared minus y squared minus z squared equals 0 was invariant for that radius of the sphere of light going out. Well, other things that are invariant that we have now seen, we had the speed of light. Speed of light in vacuum is the same in every reference frame. A second thing is mass. Mass is the same in every reference frame. And so that gives us another invariant, the mass, for Corso and Alex's Joy. There is another 4 vector that we use that is based on momentum and mass. And so you have or momentum and energy. The energy momentum 4 vector that you can do exactly the same transformations we learned on Tuesday with energy and momentum. So mass being an invariant means that we can do some interesting things with the energy. So now we're going to shift to talking specifically about some relationships in energy and relativity. So coming back to this equation, net force is, and here I have the calculus form, dp dt, the derivative of momentum with respect to time. Non-calculus, you just say change in momentum with respect to change in time. The difference in d and delta is the difference in English alphabet and Greek alphabet. The English alphabet D means that you have a tiny, tiny change, one that's unmeasurably small, whereas delta means it's a finite change, one you can measure. So they fundamentally are the same equation. Well, we learned that work is force dot change in position. And if we'd done that with calculus, it would have been integral of force dot dx. So to get the work done in relativity, all we're going to do is integrate this equation. And of course, only 2 of you are in the class where we do integrations. But here's the integration. Force is dp dt. So you have dp dt dot dx. And we just simply shifted the dt over. So we had dx dt, which is velocity, right? Delta x over delta t is velocity. And so we have the integral of dp dot v. You integrate that bad boy. It's not as easy as it looks because gamma depends on v, but you get the relationship that the change in kinetic energy through the work energy relation, net work is equal to change in kinetic energy, is equal to gamma final mc squared minus gamma initial mc squared. If we define initial as rest, then the kinetic energy should be gamma minus 1 all times mc squared. So we have an equation for kinetic energy. This is not the same as the equation we learned before. In general, would you consider this easier or harder than the equation we learned for kinetic energy before? Lauren? Okay, roughly the same looking. It doesn't look like it's that complicated. It looks roughly the same. Now we're going to go forward with this. This relativistic kinetic energy, Albert Einstein said, let's call this first term let's call that the total energy. And let's call this the rest energy. And so by Einstein's idea, we define this as saying kinetic energy is equal to energy total plus rest energy. We put a 0 there for the rest energy. And so that leads us back to the equation that we've already used, that the rest energy is mass times speed of light squared. Total energy is gamma mc squared. This actually looks kind of simple. And a lot of the calculations turn out to be simple, don't get me wrong. Some of these do turn out to be simple because those are reasonably simple equations. So, yeah, I pretty much just wrote this down, so there's no point in spending more time on this. Conservation of energy, complete. Energy is the rest energy plus the kinetic energy. Kinetic energy, gamma mc squared, rest energy, mc squared. So a reminder about complementarity. I believe we've already seen complementarity once, I think. Complementarity is a rule we invoke when we come up with some new crazy physics that's different than the old physics. And the theory of complementarity says, if I have some new novel physics theory, it better agree with my conventional classical physics in the classical realm. Classical realm is everyday, sizes, temperatures, speeds, etc. And so complementarity is going to say that, well, it says that the theories have to complement each other, that this new relativistic theory has to agree with what we've done all along, the classical physics, if we're dealing with classical physics type speeds in this case, because relativity is high speed, then the classical realm is everyday speeds. So how in the world is that going to work? What does gamma approach as you approach everyday speeds? As v is approaching everyday speed, so v over c is approaching like 10 to the minus 6. 10 to the minus 6 squared is 10 to the minus 12. 1 minus 10 to the minus 12 is approximately 1. Well, yeah. And so gamma is approaching 1, which means gamma minus 1 is approaching what Corso said, 0. And so this equation says that kinetic energy approaches 0 as we approach classical speeds. Well, 0 is not the same as 1/2 mv squared. But we had approach, so we need to look at it more carefully. So we're going to use the binomial expansion. Binomial expansion is a Maclaurin series centered around 0. Most of us aren't going to care where the binomial expansion theorem comes from. What we care about is that we can take this relationship and we can apply it to something like this. In this relationship, I have 1 minus x raised to the n. Well, my x would have to be v over c squared. And my n is the minus 1/2. And so using this Maclaurin series, the Lorentz factor, if v is very small, is going to be 1 plus 1/2 v over c quantity squared. And then I'll have more terms. But if v is small and I'm expanding in v over c squared, v over c to the 4th power is much, much, much less than v squared over c squared. And so I only take the first term beyond 1. Right? 1 is a constant. That's not interesting to me. That would have given me approaching 0. I take the first term that's not that, and I plug it in. So with this gamma approximation, then kinetic energy there is substituting in the binomial expansion. And you'll notice I have a 1 plus something minus 1. 1 minus 1 is pretty trivial. They add up to 0. And I'm left with 1/2 v squared over c squared mc squared. Cancel the c squareds. And I have 1/2 mv squared. Does that agree with classical physics? Okay. 3 people said it does. Okay, there's a 4th person. Guessing everybody else doesn't believe that agrees with classical physics? Well, those 4 people were correct. It does. That's the classical physics equation for kinetic energy. We learned it first semester. Kinetic energy is 1/2 mv squared. So we have agreement, we have complementarity in the region of overlap. That's important for our physics. We do not want our physics theories to be at odds with each other, to disagree. So it's important that we can go and show, yes, they do agree that we have kinetic energy is 1/2 mv squared in slow speeds. Now we're going to come back to the radioactive decay of carbon-14 to nitrogen-14. And here I said it releases 156 kiloelectron volts of energy. It's not what I calculated before. I don't think I made a mistake, but I must have. Right, because I had 0.669 Didn't I? Where is it? Could I have done that subtraction wrong? I don't think so. I suppose I shouldn't worry about it in the middle of class, but I'm going to. Nope, did it right. So I cannot explain. Maybe I wrote down the wrong mass number. Anyway, we'll stick with the number that's here. It says the radioactive carbon decay of carbon-14 to nitrogen-14 releases 156 kiloelectron volts of energy. If all the energy released appears as the kinetic energy of the electron, how fast is the electron moving? If I have an electron with a kinetic energy of 156 kiloelectron volts, how fast is it moving? What do I need to do? How do I find the kinetic energy, or find the speed if I know the kinetic energy? That's going to be part of the way. I need to start with what is the equation for kinetic energy. That was the classical, but this is going to be relativistic. Yes. That's my equation. Now I need to solve for speed. Where's speed in that equation? Not in C. C is the speed of light, not the speed of my electron. It's in gamma, because gamma is 1 over the square root of 1 minus V over C squared. So I'm going to need to first find gamma, and then from gamma find the speed. So now, Corso, how do I solve for gamma minus 1? Because you'd already said this, that's why I called in. From this equation here, how do I solve for gamma minus 1? So I get gamma minus 1 equals 156 kiloelectron volts over 511 kiloelectron volts per C squared times C squared. So 156 over 511 gives me 0.3053. So gamma is equal to 1.3053. Now that I have gamma, how do I find V? You've had to do this over and over. Well, you've had to do it a few times at least. How do I find V from this equation? Okay, let's square it. Next step. Next step in this class, we're astute enough at math that we know that 1 minus V over C quantity squared is equal to 1 over gamma squared. Then we flip sides for these two things. And finally, we square root both sides. We use this enough that that's a useful equation to know. It's not going to be given on the exam because it's just inverting that starting equation, but it's pretty useful because a lot of times you have to go from gamma to V. Yes, ma'am.
For the test, would it be fine just to write that equation, or do you have to show how we got
In this case, yeah, you could just write that equation because it's just inverting another one. So, you write down this equation and then you say, so this equation. And I'm happy with that. And so now we can actually do our calculation. V is equal to C times the square root of 1 minus 1 over 1.3053. Notice 1 squared is just 1, so I expanded where I'm squaring. Yeah, I screwed up on my calculator already. So that electron is going 64% the speed of light. At this point, we know, yes, I had to do it relativistically. If gamma, as soon as we get gamma is not equal to 1, we know that we have to do it relativistically. And so here we found the speed of the electron that's produced by that radioactive decay. It's going really fast. A couple more equations here. Relativistic energy relationship. This here is a new equation. That new equation actually comes from the invariant that I mentioned, the energy momentum invariant. So the total energy squared is equal to the rest energy squared plus momentum times speed of light quantity squared. That's another equation that we use in solving energy problems. I could have used this equation earlier in calculating the, it actually wouldn't have been easier for me at all to calculate the speed the speed of the electron. But there are cases where this equation is going to make it much easier. If it asks what's the momentum, you can just use this equation to relate the total energy and the rest energy, and you know the momentum. So if you take E, we know that E is equal to kinetic energy plus the rest energy. So if you square it, E squared is equal to kinetic energy squared plus 2 kinetic energy times E0 plus E0 squared. Got to move that so it doesn't run into my equation. And so if I replace the E squared in this equation with this long thing, that will simplify this equation to this, where this K is kinetic energy. And so 2KE means 2 times kinetic energy times rest energy. So this equation that's in the middle is just a composite of the first equation, the total energy is kinetic energy plus rest energy, and this new equation that says the total energy squared is equal to the rest energy squared plus momentum times C quantity squared. The last thing of importance for today, I believe, is defining momentum. We already have momentum is equal to gamma mv. But what if we have something that has a rest mass of 0? If it has a rest mass of 0, then E0, the rest energy is 0. And so this equation here becomes the energy squared is equal to momentum squared C squared. So solving that for momentum gives you, right away, momentum is equal to E over C. Now, what's different between this equation and this equation? The difference in the equations there, I trust, is that one's a vector relation and one's not. And so I had to do a little work there. But this here is, well, this here is specific to the momentum of particles with zero mass. What particles have zero mass? I already said it, but just to make sure. There's only one. Photons, particles of light. So for particles of light, the momentum is their energy, which we'll learn is HF, divided by the speed of light. Okay, we're at time. Have a happy Sabbath, y'all. I'll see you next